Okay, so welcome everyone to the Infosys Chandrasekharan colloquium. So very happy to have Barbara Schapira back for her second talk on counting closed geodesics on non-compact hyperbolic surfaces. Barbara, please go ahead.
Thank you for this second invitation. Okay, today I would like to speak about counting closed geodesic on hyperbolic surfaces, but in the case where the surface is non-compact and even of infinite volume. So um, maybe we will first begin with by recalling what we discussed last week. What we discussed is that okay, if you have a try to draw a picture when I speak, you have a compact hyperbolic surface, and you want to count periodic orbits. You begin with an equidistribution result. Each time you have a periodic, a closed geodesic like that, you consider the measure, that's the periodic geodesic, and you consider the measure, the Lebesgue measure on the periodic orbit, which is called mu p, and you normalize it as a probability measure, mu p divided by the length of the periodic orbit, and p of t is the set of periodic orbit of length at most t, and if you average you consider the sum over all periodic orbit of length at most t of all these measures divided by this normalization, it converges to a certain measure, which is called the Bowen-Margulis-Sullivan measure. Uh, Implicitly here, it's normalized to be a probability measure. And once you prove this theorem, you integrate the constant function equal to 1, and it gives you that the number of the cardinality of P of t, the number of periodic geodesic of length at most t, is equivalent to exponential ht over ht, and where h is the topological entropy of the geodesic flow that I don't want to define too precisely. And if I try to recall some of the discussion of last week, the main ingredients of the proof were first the product structure of the geodesic flow, which is easily seen geometrically when one says that given a vector v, which is a tangent to the hyperbolic disk, it has two endpoints v minus and v plus, so that I remind you that the unit tangent bundle of the hyperbolic disk is homomorphic to a product S1 times S1 minus the boundary, the diagonal, so, times a set of parameters, of real parameters. And this product structure leads to mixing, topological mixing, but also mixing of a nice measure, which is called the Bowen-Margulis-Sullivan measure, denoted by BMS, and which is a nice measure which is equivalent to a product in this coordinate. And the last ingredient that I almost skipped last week is that the constant function 1 has compact support. And if you remember the argument last week, everything happened in small boxes which had a product structure with a stable direction, the unstable direction, and the flow direction. I don't want to do the argument again, but and implicitly, equidistribution of periodic orbit came from the fact that any continuous function with compact support can be approximated by indicator function of this kind of boxes. And so that in fact, when in this kind of statement, equidistribution means that for all map phi, which is continuous with compact support on the unit tangent bundle. When you integrate this function phi with respect to this finite measure, it converges to the integral of phi with respect to this probability measure. And in particular, when you integrate the constant function equal to 1, when the manifold is compact, the constant function equal to 1 has compact support. It's completely obvious what I say. And it leads to this counting for all of them. And the point is that when the manifold is not compact, the constant function equal to 1 does not have a compact support, and so that it cannot be approximated by indicator function anymore. And so our program today will be to state the analogous result in the non-compact case. You will see that there will be a change in the statement. And then we will explain more in details what is this Bowen-Margulis-Sullivan measure and give a finiteness criterion for this measure, because in the non-compact case, this measure could be infinite. And when it's finite, we will explain how to go from a convergence theorem for continuous map with compact support to continuous bounded maps. And now we will conclude the counting argument by arguing that the constant function equal to 1 is continuous and bounded. So is it maybe, okay, it will, all these steps will be more clear during the talk, but as last week, please don't hesitate to ask questions during the talk, particularly if it's going too fast or something is not clear. Okay, so the first problem is the following. Okay, I draw some pictures of some non-compact manifold, but take, okay, this maybe one of the simplest examples of a non-compact manifold is this one. It's an infinite cover of a compact hyperbolic surface. Infinite cover means that, okay, you imagine that you cut your compact hyperbolic surface along a simple closed curve. So it gives you some elementary piece like that. And of course, this curve and this curve are the same because you cut here. And then you glue them infinitely many times, and you get this surface with infinite genus. And then if you consider any fixed number t, the number of geodesics of length less than t will certainly be infinite, because you have infinitely many geodesics of same length for each non-trivial length. And so you could think that you are done. Nothing can be say more intelligent than the fact that the cardinality of P of t is infinite. For any once again, for any length, for t large enough, the number of closed geodesic of length at most t is infinite. And okay, it's a little bit sad because it seems like nothing can be said more. Okay, this simple example of an infinite cover seems really trivial, but if you imagine any complicated non-compact surface, the same thing will happen. You see here, I have many curves with bounded lengths, and I can really easily imagine many non-compact hyperbolic surfaces where the number of closed geodesics of length at most t is infinite. So either you stop thinking to the problem or you find something more intelligent to study. And the point is that when you have a non-compact, an infinite volume non-compact manifold, typically my Z cover of a compact hyperbolic surface, there is a natural normalization, which is to say, okay, if you count the number of closed geodesics of length at most t, it's infinite. But now we will normalize by choosing a given compact set here. That's a compact set, or maybe with yellow is a better idea. I'll change. And you choose a compact set, and okay, there is some assumption. You imagine that your compact set is non-trivial in the sense that its interior will intersect at least some closed geodesic, and you will denote by pk of t the set of closed geodesics of length, it's not t, but at most t, that intersect your compact set. It's okay, it's a normalization which leads to the following theorem that we proved with Samuel Tapie years ago. Okay, you consider, during the talk, it's it's as last week, I speak about hyperbolic surfaces, but everything is true for negatively curved Riemannian manifolds of any dimension. And even I had a question last week, it's also true for cat -1 in the cat -1 setting, but I don't want to, I just want to keep my talk on hyperbolic surfaces where our result is already new. Okay, so I consider a negatively curved manifold, and my only assumption is that this Bowen-Margulis-Sullivan measure is finite. That's really a key assumption. And then normalizing to the set of closed geodesics that intersect a given compact set, I have the same counting result, that the sum of periodic measures on periodic geodesics that intersect my compact set divided by exponential ht over ht converges to the Bowen-Margulis-Sullivan measure. And what is interesting and important here is that it is not in the dual of continuous function with compact support, but in the dual of continuous function with which are bounded. So it's much stronger in general. And in general, if you are used to convergence problems of measures in the non-compact setting, going from the convergence over continuous function with compact support to the convergence of a bounded continuous function can be hard. Okay. And so as in the preceding talk, we get the corollary that integrating the constant function equal to 1, we get the counting corollary that the number of periodic geodesics that intersect K and have length at most T is equivalent to exponential HT over HT. And you see, it's funny because, okay, K is any non-trivial compact set, non-trivial meaning that its interior intersects some closed geodesic, and the statement does not depend on such a compact set. It's quite funny. So let me explain to you how this theorem can be proven. So first I have to explain something to you about the assumption and finiteness of the measure. And to explain it to you, I have to give you some more details on what is this measure, this Bowen-Margulis-Sullivan measure. Oops, sorry. So how do you construct this measure? So as I said, I consider hyperbolic surfaces, but everything is true in a much more general context. So any hyperbolic surface, called here S, is a quotient of the hyperbolic disk by a discrete group gamma. And instead of constructing a measure on the unit tangent bundle of our surface S is my surface, and we don't consider, we don't build the measure directly on T1S. We we use the product structure on the unit tangent bundle of the hyperbolic disk, and we will use the fact that, okay, my surface S is the quotient of the hyperbolic disk by a discrete group gamma, and therefore its unit tangent bundle will also be the quotient of the unit tangent bundle of the disk by my discrete group gamma. And therefore, instead of constructing a measure here, we don't construct a measure here. We construct a measure here on the unit tangent bundle of the hyperbolic disk, which will be, by construction, invariant under the group gamma. And so it's the same than constructing a measure here. So the point is that on the unit tangent bundle of the hyperbolic disk, we have this product structure. As I said, it's just saying that given a vector, it defines a geodesic which has two endpoints in the bundle. Okay. And
Barbara?
yes.
There's a question in the chat, which is that is the condition that the BMS measure is finite for hyperbolic surfaces, is it the same as being geometrically finite?
No, I will discuss that. And precisely that's why it's interesting, because, okay, I should have said that this was known for geometrically finite surfaces or manifold. I'm sorry that I didn't mention that. And I'm not sure who I should cite first for this case. Certainly Roblan is in the story, and maybe I forget someone, but okay, I'm sorry that I probably missed some people in the geometrically finite case. What is geometrically finite? It's essentially saying that your surface has finitely many ends. For example, finite and some ends. I'm sorry that my picture is really bad. You can have some ends which have finite volume, and you can have some ends which have infinite volume, and you can have a part with topology in the middle. And okay, this is a geometrically finite surface. Maybe my picture is not clear. And this result was known, and it's the only case where it was known. But if I come back to this picture, I will discuss that. But this example, for the moment, it's not explicit because it's just a picture. It's an example of what we called with Samuel Tapie, we call that Ancona-like surfaces. And it gives plenty of examples of geometrically infinite surfaces where the Boyle-Margulis-Sullivan measure is fine. So our assumption is much more general. But I will discuss that in a few minutes.
Thanks.
Okay, so I come back to my construction of measure. So I use the product structure, and in this coordinate, I say I, but the construction is due to Sullivan. This measure, this Boyle-Margulis-Sullivan measure, can be constructed in 3 different ways. And what I describe now is a Patterson and Sullivan construction. Patterson and Sullivan construction. And okay, you build a measure first. Okay, you want to build a measure which has a product structure, and this measure which will be equivalent to a product. Nu times dt. dt is the Lebesgue measure on the real component, which leads to the fact that this measure will be invariant under the geodesic flow, because the geodesic flow is just the action by translation on this real component. It just pushes vectors along their geodesics. So, and this measure nu is a measure on the boundary. And okay, you could dream to build a gamma invariant measure, gamma being the group here. Okay, but it's a simple exercise to show that it does not exist, but okay, still you build the measure nu on the boundary as a limit of orbital measures. You construct a measure whose support is the full orbit of gamma. All these points are the point of the orbit of any point gamma O by the group gamma on the disk. And as the group gamma is a discrete group, this orbit accumulates on the boundary. And okay, you have a parameter here, S, and you begin with a large parameter S, and then you make the parameter decrease to a kind of critical exponent, which is called the critical exponent of the group. And you can show, of course, you have a certain amount of lemmas to prove, but it's a classical construction that when S decreases to this critical exponent, then your measure converges to a measure on the boundary. And it's normalized so that nu is a probability measure on the boundary. And it will be, by construction, as it's a limit of orbital measures, it will be not invariant under the group, but quasi-invariant. It means that if you push this measure by any element of the group, you get a measure which is equivalent to the first one. And this critical exponent is, in fact, it's easy also to show that it's the exponential growth rate of the orbit gamma. So delta gamma is the limit of 1 over r log of, I should maybe have written that before, the cardinality of the orbit inside a ball of radius r. Okay, I don't want to spend too much time on this construction, but it's a classical construction, well studied, and there's no problem. Okay. And there is a theorem which was first proven by Sullivan, but I should add in the highest generality, it has also been proven by Otal and Peignet, that the critical exponent of the orbit of a group coincides with the topological entropy of the geodesic flow. So what I called H at the beginning and in the statement. And there is also something which, okay, I will not use it explicitly maybe in the sequel, but it's very useful in all the proofs of all the intermediate statements that I will use, is that, okay, my measure nu on the boundary is a limit of orbital measure, and therefore when you consider small sets in the boundary, which are called shadows, shadows because it's a set of points which are in the shadow. Consider a small ball here, and you imagine that there's light coming from here, and you look at the light rays going from geodesic, starting from the point here, and if you have a ball here, this light will not pass through the ball, and you will have a shadow here of the ball. And the classical Sullivan's shadow lemma tells you that the measure of a ball far from the point O, here you have a certain distance from O to the point Y, and the measure of such a shadow decreases exponentially with this distance. So usually it's used here, okay, I could have stated it's a shadow of a ball of centered at the point Y. The measure of such a small ball, the shadow of this ball, when the ball is far, decreases exponentially fast with the distance from O to 1. And okay, this is equivalent, this geometric lemma is equivalent to something that we said last week when we said that this Boyle-Margulis-Sullivan measure had a local product structure in the stable, unstable, and okay, I'm sorry that my picture is bad today. I had a measure, I described it as a measure which had a local product structures which could be decomposed in this measure in the stable direction, in a measure in the unstable direction, and the Lebesgue measure on the flow direction. And these measures satisfied a relation that when you push them by the geodesic flow in the stable or unstable direction, you got these exponential ht or exponential minus ht expansion or contraction factor. And okay, this shadow lemma is the geometric equivalent of this. Okay, that's maybe a technical point, but it's in fact important in all the hidden arguments of what I will describe today. Okay. Okay, now I would like to discuss the finiteness of this measure. And before discussing the finiteness of the measure, I would like to recall you maybe something. Okay, I don't know the general culture of the audience, but there is a lemma in ergodic theory, which is a very elementary lemma, I insist. It's important for it because it's useful, not because it's difficult. It asserts the following: if you have a dynamical system X and you have a measure M and a dynamical system T, and okay, you have the measure is invariant, and you assume that it's ergodic and conservative. Conservative means that, okay, maybe it's not finite, but the conclusion of Poincaré recurrence theorem is true. That is that if you have a set A of positive and finite measure, almost every orbit will come back infinitely often. And then this lemma asserts that the measure of the full space X is equal to the sum over n of n times the measure of an. And what is an? In fact, okay, you have your set A, that's very, I don't know how to qualify this picture. But imagine you have your set A, and it's classical that you divide A in return times. Partition means that, okay, you have a set A1, which is a set of points such that at the next step, T of X will be inside A. A2 is a set of points X such that T of X is not in A, but T2 of X is in A. So, and so T of X is somewhere, but not in A. And so that is T of E2. You have A3, which is a set of points which come back after 3 steps. So you have T of A3 and T2 of A3, which are disjoint, because if they were not disjoint, then you would not be in A3. Okay, that's an exercise, etc. And AN is a set of points which needs n steps before coming back to A. And if you look at this picture, you realize that this picture is a direct proof of this assertion. The total, as the measure is invariant, the total measure of the space is a sum over n of all the measure of an and its images. And as you have n copies, okay, it's the sum over n of n times n of an. And in fact, this elementary statement is the only place where you can, to my knowledge at least, it's the only statement where you can see on a quantity that can maybe be computed or not, if a measure is finite or not. because, okay, here you have a series, and of course, if the series converges, the measure is finite, and if not, the measure is infinite. Okay. And that is something which is used to characterize the finiteness of Boyd-Margulis-Sullivan measure. In fact, with Vincent Pitt, a few years ago, we characterized, I will explain this, okay, maybe it's not, I comment first the statement. We characterized the finiteness of the Boyd-Margulis-Sullivan measure by the following result. This measure is finite if and only if it is first ergodic and conservative, to apply the CAC lemma, and then a certain series converges. And you have to think to this series as a series of kind of return times inside a good set. And what is a good set? Okay, we had, okay, in the spirit, it's just a CAC lemma, but we had to reinterpret CAC lemma in a geometric situation. So instead of a Borel set A, we will consider a compact set K here. And we will, instead of the partition AN inside in return times, the return, what is called the return time partition that is used in the partition that is used in CAC lemma, we introduced this set, which is a set of element gamma, such that when you look at the segment from O to gamma O, this segment is an excursion outside gamma, outside K, meaning that in the middle, it does not intersect other copies of K. It means that if you look at your surface, which is the quotient of your disk by the group gamma, okay, I don't want to draw a too precise picture, but you have a certain compact set here, K, and gamma is in this set gamma K, means that the geodesic segment from O to gamma O in the quotient, it starts from K, it goes outside and comes back after a certain time at the same point, sorry. And in the middle, it does not come back. So this set gamma K encodes the set of excursions outside K. So, for example, this G here means if you look at the segment from O to GO, it starts from K, it will go outside, cross again a copy of K, go outside and cross again a copy of K. It will give you a loop which starts from the same point, goes away from K, goes back, goes away from K and goes back. That's not an excursion. That is an excursion, that is not an excursion. That is a concatenation of excursion, and the red one is a concatenation of excursion, and the blue one is an excursion outside.
And what's the quantification for K? It's any finite measure, positive measure set for some K of positive measure, or what is how do you quantify? How do you quantify for K? Is it this inequality is true for some positive measure K? Is that the condition? This theorem that you've quoted?
I'm sorry that I don't hear well the question.
I'm saying, do you quantify it for all K or for some K?
For all K, for any compact set, I define a set, a subset gamma K of gamma. It's a subset of gamma. Is it? Was it your question?
My question is about the theorem that you stated. That MBMS is finite if and only if it is ergodic and conservative, and this statement and this sum.
Set.
Oh, there exists. Okay, yeah.
Which is non-trivial in the sense that its interior
Positive
has
measure
to intersect at least a closed geodesic.
Yeah.
And this sum is finite.
Thank you. Thank you. Yeah.
Sorry that I have a technical problem, so I don't hear you very well. But it's not you, it's everybody.
Thank you. Yeah.
Okay. And so, okay, what I would like to emphasize, okay, is that, okay, this criterion that we got with Vincent Pitt is really a geometric reinterpretation of CAC lemma. And the proof is maybe technical, but it's really because there are geometric technicalities to come from a discrete dynamical system to a continuous one, and etc. But it's really, in the spirit, it's just a CAC lemma. And the important point in our work was to introduce this set, which encodes all the excursions outside a given compactor. And okay, maybe I will continue now. And okay, we further pursued this study of manifolds with finite Bowen-Margulis-Sullivan measure with Samuel Tapie, and we gave a sufficient condition to get examples with Bowen-Margulis-Sullivan measure which is finite. It's a sufficient condition, it's not equivalent. So recall the criterion was that the measure is finite if and only if it is ergodic, conservative, and a certain sum over gamma k of a distance I will not have enough place, exponential blah 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 is finite. That was my criterion of the last slide. Okay, and what we claim, which is not so difficult but not immediate, is that when the growth rate of this subset gamma k is strictly less than the critical exponent, then this measure will be finite. This assumption trivially implies that the series converges, but it does not trivially imply that it is ergodic and conservative. But it's still true. But it's true. And this criterion is much stronger a priori than this conclusion. But okay, we have not so many examples where the measure is finite and this criterion is not satisfied. And at least this criterion, okay, it's very efficient because it led us to many non-trivial examples where the Bowen-Margulis-Sullivan measure is finite. And of course, compact manifolds are inside and geometrically finite hyperbolic manifolds also. But we got also two other categories of examples, what we called Ancona surfaces, because, okay, there is an unpublished note of Ancona building one example where the Bowen-Margulis-Sullivan measure was finite, but okay, he did it with spectral analysis of Laplacian, and he didn't publish it anyway. So, and reading his paper, we realized that, okay, his construction can be modified geometrically to get plenty of examples. And the strategy is, for example, okay, is the following. We know how, okay, I don't know if I have to, okay. I'm not sure to have time to develop how to build such examples, but the idea is to start with a compact hyperbolic surface, let's say S0, to build an infinite cover, which is a F2 cover, F2 being the free group with two generators. Let's say S0 hat, which is I'm not able to draw on my file F2 cover, but it's possible to build a F2 cover S0 hat of S0. And okay, the critical exponent or the topological of entropy of S0 will be equal to 1, that is known. And it's also known that as this cover is non-amenable, that's something that I don't want to explain here, the critical exponent of S0 hat is strictly less than 1. That's okay, that's well known, let's say. And now I start from this S0 hat, and it's also known that all hyperbolic surfaces are built from building blocks which are called pairs of pans, which are small pieces like that. And so everywhere here you have small pairs of pans like that, which are glued to other pair of pans, etc. I'm sorry, I'm not sure that my picture means something for you. Anyway, you can decompose this surface S0 hat into infinitely many pairs of pans, and you will take one pair of pans, just one, and you will pinch a little bit the boundary components of one pair of pans, and one can show that doing that, the entropy of the new surface becomes closer and closer to 1, but it does not change if the compact set is something like that, let's say K. It will not change the critical exponent of the gamma K, because this thing depends only on what happens outside the compact set. And therefore, the critical exponent of the gamma K is at most the critical exponent of the initial surface, which was S0 hat, and which is strictly less than 1, and the critical exponent of the final surface, when I pinch more and more here, it will be close to 1. And so you will easily build plenty of examples where you will get this strict inequality. There is also another construction, but if I give details, I will really lose the aim of my talk today. So it's just to say that, okay, in fact, there are several non-trivial examples. Non-trivial meaning geometrically infinite, where the Bowen-Margolis-Sullivan measure is finite. So does it answer your preceding question on this assumption?
Thanks.
Okay, so I feel I don't pursue on this assumption now. It's just I said that, okay, I have a criterion which characterizes finiteness of the Bowen-Margolis-Sullivan measure, and I have plenty of non-trivial examples where this assumption is satisfied. And now I want to prove the theorem. Recall that we are speaking about equidistribution of periodic orbits and counting. So the point is that what we did last week didn't really use the compactness of the manifold. We just worked on boxes, on small boxes, which had a product structure with a stable direction and unstable direction and flow direction. And so it still works, but it gives the following statement that, okay, if you have a negatively curved manifold, and if the Bowen-Margolis-Sullivan measure is finite and normalized to be a probability measure, then when you look at the measure over all periodic geodesic of length at most t divided by exponential ht over ht, this converges to the Bowen-Margolis-Sullivan measure in the dual of continuous function with compact support, just by an approximation argument of compactly supported functions by indicator functions of boxes. The argument of last week didn't really use compactness. And so we will use this theorem, which is really non-trivial. And what it remains to prove is, in fact, okay, we are interested in geodesics which intersect a given compact set. And so I call MT this sum over this average over all periodic geodesic of length atmos T, and I call MTK this average over all geodesics of length atmos T which intersect K. And I know that MT converges to the Bowen-Margulis measure in the dual of continuous function with compact support. The first point is that I want to prove the same for MTK. I want to prove that MTK converges to the Bowen-Margulis-Sullivan measure in the dual of continuous function with compact support. And the second step will be to show that this convergence holds in the dual of bounded continuous function. Is it okay for the strategy? And okay, and for the step one, there is a natural way to try to do that, is to show that, okay, this measure MT converges to the good measure. And I want to prove that this one converges to the good measure. I just have to study the difference between the two measures. Okay, that's exactly what we will do. Okay, I use the terminology vague convergence to, often people use the terminology of weak convergence, which is not completely explicit. And so I will use vague convergence to speak about convergence in the dual of compactly supported continuous function, and narrow convergence in the dual of bounded continuous function. Okay, so to prove that the measure at MTK converges to the Bowen-Margulis-Sullivan measure, as I said, we know that the measure MT converges to the Bowen-Margulis-Sullivan measure, and I just want to prove this. It's enough to prove this. Okay, we study the difference of measures. Okay, and we want to prove that this difference goes to 0 in the dual of continuous function with compact support. So consider such a function. It has a compact support, and so let's say that the support is inside KR, where K is my initial compact set, and KR is the R neighborhood of K. So here you have the distance R. And so, in fact, you forget your map phi because it's easy to check that if you average, you consider the integral of phi over periodic orbits that intersect K, and the difference with the average of phi over all periodic orbits of length atmos T, it's the same as the average of phi over all periodic orbits that intersect K minus the average of phi over all periodic orbits that intersect KR. Because if you consider a periodic orbit that which does not intersect the large compact set, then the integral of phi will be 0. And then, okay, I should add absolute values here because if not, it would be okay. And then consider this difference, and then, okay, maybe I forgot some details, but it's you have the normalization constant here, and the difference, what is it? It's a sum over all periodic orbit of length, say around T instead of atmos T. That's a technical point, which intersect KR but not K. Okay. So the important point is to understand what kind of periodic orbits intersect the large compact set and not the small one. Okay. And now for these periodic orbits which appear in this sum, you count the integral of phi. Okay, maybe somewhere you have a norm of phi, but you don't care. I will forget it. And so you have to understand the length of the periodic orbit intersected with KR divided by LP. It is sum over all these times spent in KR divided by the total length. But the total length is essentially T. Okay, so this one cancel with this one. So you get up to constants that I forget, you get exponential minus ht times the sum over all these geodesics that intersect KR and not K of the length, the total length of this time spent in KR and not in K. Okay, and oops. And it's the strategy is to understand, one understands often things better in the universal cover. So universal cover means the hyperbolic disk. So here I am in the hyperbolic disk, and I have my geodesic which intersect KR and not K. I draw it like that. So it goes through KR, goes outside and goes back through KR. And the point is that for each piece of geodesic crossing KR and not K, we consider a geodesic segment from O to this piece of geodesic, and then to this piece of geodesic until it comes back to KR, and then this piece of segment. And this is a hyperbolic geometry fact that this can be approximated by a piece of geodesic from O to gamma O here. And this piece of geodesic from O to gamma O will go outside K and outside KR and comes back to KR and then to K. And so it will lead to an element of gamma KR. So each red piece here will lead to an element gamma in gamma KR. I don't have time to really convince you that I don't cheat, but I really don't cheat. And you get a bound. We were counting exponential minus ht times this sum over all periodic orbits intersecting KR and not K of length T, of their red length. And this sum is bounded from above by the sum over all gamma in gamma KR with distance from O to gamma O roughly T of, okay, these terms, these it should be red, these red lengths, the length of P intersected with KR is certainly smaller than the total length. So this bound is really a stupid bound. That is really much smaller than that. And the exponential minus ht, T is essentially the distance from O to gamma O. So it gives you this term. And as we assumed the Boyle-Margolis-Sullivan measure to be finite, this last sum is smaller than the remainder of the series which appeared into the criterion of finiteness. So this, okay, what I'm saying is that this is smaller than the sum over all gamma in gamma KR, such that the distance is larger than T of the same thing. And then, okay, the measure is finite if and only if it's ergodic and conservative and this series converging. So this is the remainder of a convergent series so that it goes to 0 when T goes to infinity. And so I got my first step, meaning that okay, what I wanted to prove is proven. This difference goes to 0, and as this one converges to Boyle-Margolis-Sullivan, this one also. And my last step, I should conclude the talk with that, is the second step, that I want to prove, I have 2 minutes left to do that. I want to prove that this sum over or this average of periodic orbits intersecting K converges to Boyd-Margulis-Sullivan measure, not only in the dual of compactly supported functions, but also in the dual of bounded continuous function. Okay, and when you already know that a sequence of measures converge in the dual of continuous function with compact support, it's classical. It's really a classical exercise to show that it's enough to prove a statement which is called non-divergence or tightness. I mean, if you are able to prove that for all epsilon, there exists a compact set, say, KR, such that for all t large enough, the measure of KR is at least 1 minus epsilon, then you will be able to prove that the above convergence falls in the dual of bounded continuous function. That's classical exercise for convergence of measures. So what we want to prove is this non-divergence or tightness result. So for given epsilon, I want to find a compact set that I can consider to be a R neighborhood of K. That's easier, but it's just a technical point. And such that for all t large enough, the measure of KR is almost 1. And so here, it will also be a proof with geometry consideration. Here, I want to consider all periodic orbits of length roughly t, which appear in this sum. So they intersect the compact set K. But I want to show that for R large enough, the measure of the complement of KR is small. On my picture, it's not clear, but the point is that for R large enough, the true picture is that KR is really huge, and the geodesics, when they have to spend time in K, then they take a lot of time in KR. They go maybe a little bit outside, but not so much, etc. And at the end, the proportion of time spent outside KR should be small. So that's what we want to prove. It's not clear for the moment. And so maybe I have a few seconds to give you the hint. So in fact, as before, for each geodesic appearing in this sum, the quantity that we want to estimate is essentially exponential minus ht times the sum over all periodic orbits of length roughly t, which intersects a small compact set of the length of p inside the complement of kr, so the red thing. So we want to bound this sum, and as before, we lift things to the universal cover, and we try to understand what happens outside of KR. And in fact, our geodesic, when it's outside of KR, we will write all our lift all our closed geodesics and understand them as a concatenation of excursions outside KR. And so we will write them as a sum over all element alpha of gamma KR. So here you have the point O, and here you have alpha O, and alpha encodes an excursion outside KR. And here I hide a little bit more computation. It's a little bit more subtle, but it's still true, and I don't cheat, that this sum is bounded from above by the sum over all such alpha with distance from O to alpha O is at least the distance to go from K to KR complement. So here, recall that KR is the R neighborhood of K. So here you have R. And here you have R also. So the distance from O to alpha O is at least twice the distance R. And so it's bound, okay, this first sum is bounded from above by the sum over all alpha, such alpha with distance from O to alpha O greater than 2R of, okay, the red distance is less than the distance from O to alpha O. And okay, the exponential minus HT, you can bound it by this exponential minus delta gamma times the distance from O to alpha O. That's a little bit more subtle because a priori T is the distance from here to here. But you have a lot of, the point is that you have a lot of periodic geodesics going from here to here, or from here to here, or from here to here, etc., which correspond to the same alpha. So that's why you can get this bound. Okay, there are some things hidden there. I guess that was my last slide. Or yes, that was the slide of us. So I will stop here, and I thank you for your attention.
Let's thank Barbara for the lovely talk.
Maybe I will put my micro case because I don't hear you.
So let's thank Barbara for the lovely talk. Are there any questions?
Yeah, so there does not seem to be any restriction on dimension either in your statement, right? So this is true for arbitrary dimensions?
Yes, that's what I said at the beginning, but I didn't want to insist because I don't know the background of the audience. But where is our statement? This statement here is true for any manifold of with negative curvature, any dimension. Variable negative curvature is allowed also. When you say variable negative curvature, you need to ask that the derivatives of the curvature are bounded, because you can have troubles with entropy if it's not the case. It's also true in the cat-1 setting. And if you stay in the Riemannian setting, if people are interested in, it's also true with potentials and Gibbs measures instead of Born-Margulis. I don't know if it answers your questions.
Yeah, thanks. And so you did mention this. Can you just repeat the characterization of finiteness of the BMS measure?
Yes.
There was some, yeah.
Of course. So it relies on this well-known Cat-Klein ergodic theory, which is really an elementary lemma. And so this criterion is here. Oops. Maybe I will. There are too many things on my slides. The Born-Margulis-Sullivan measure is finite if and only if it is ergodic and conservative, and for some compact set, which will be non-trivial in some natural sense, this sum is convergent.
Okay, thank you.
And this criterion was known, maybe I could say that if the manifold M is geometrically finite, it was a criterion known by Dalbo, Otal, and Pellier. But in the geometrically finite case, they didn't have this concept of gamma k. But if you are familiar with geometrically finite manifolds, then the important thing is the study of parabolic subgroup. And when M is geometrically finite, one can show that gamma k is a union of copy of a parabolic subgroup.
Yeah, thank you. Yeah.
So this criterion was already known in this particular case. Other questions?
So are there any results known in high rank?
In higher rank? in higher rank, okay, no. First, a remark, which is also relevant in rank 1, is that, equidistribution of periodic orbits really needs, where is it? Really needs the Bowen-Margulis-Sullivan measure to be finite to have a meaning. Okay, but there are examples of counting results in some rare cases where the Bowen-Margulis-Sullivan measure is infinite, but you understand well things. So I don't know if Mark Policott is still here, but for example, for abelian covers of compact hyperbolic surfaces, I guess that he knows that. Okay, is Mark here or not? He could help to say us that he proved that in the past. No, he's not here. He was there at the beginning. Okay, when there are some cases, okay, this infinite cover example is a typical example where the Bowen-Margulis-Sullivan measure is infinite. So our main theorem does not apply. However, you can get counting because you understand well the compact underlying manifold and the group acting on the cover. And then you have I don't remember the precise statement, but you have statements in such cases where you have it's exponential ht divided by some polynomial which is larger than usual. And probably it's something due to Politico-Sharp, or I don't know. I would say Politico-Sharp, but I'm not sure about the reference. And there are other cases. For example, there is a student of Samuel Tapie and Marc Peignet, Pierre Vidotto, who got results where in other situations, in variable negative curvature, there are strange examples where you have geometrically finite manifolds with infinite Bowen-Margulis-Sullivan measure. That exists, and in these kind of strange examples, he could get counting results because it's a geometrically simple and strange dynamical example, and so he could get counting estimate. So when that was just a preliminary remark before speaking about the higher rank. So in higher rank, the equivalent of, okay, they are equivalent of the measure nu in the Furstenberg boundary. So when you try to get when you try to use the product structure, then it's possible to, in certain situations, for example, Schottky group, images of another representations or things like that, you can get a Patterson measure here. And I think that, okay, it's a higher rank, it's a domain with very active community, and so there were recent results on this. So there exists a construction of the Patterson measure on the boundary. There was a preliminary work of before the recent works, there were 3 people that I would like to cite: Gabriele Link, Jean-François Klein, and Xavier Thirion, who was a student of Marc Peignet, who constructed things like that in particular cases. And the point is that the product structure gives you here, in higher rank, you have to replace the real component by a flat in the veil chamber. And then if you build the product measure, here you have, I don't know how, the A probably for A in the flat that you chose. in the veil chamber, and then you will get an infinite measure.
Right.
But still, as in certain situation in rank 1, it's not because it's infinite that you cannot hope some counting result in some cases. But it needs some mixing estimates for infinite measure, which are very, very particular phenomena. I mean,
Right.
for the moment, it's not so well understood.
Oh,
So,
thanks.
but the main theorem, which is equidistribution of periodic orbits, it's not clear what does it mean, a periodic orbit.
Right.
This one has more hope.
One more question. So you talked about Ancona surfaces. So your definition is that these are covers of closed surfaces or say finite volume surfaces corresponding to what subgroups of critical exponent strictly less than that of the group? Or I missed the definition of your Ancona surfaces.
Yes, it's because I didn't define it. I come back to the picture, maybe. We said that not Ancona surfaces, but maybe Ancona-like surfaces. It's just, oops, what I did. Where is my? Do you? I lost my screen. Sorry. You still see my screen?
Yeah, we can see your screen.
Okay, I just made something strange. Okay, here, my how can I say that? It's not really a definition. I must say that I don't even remember exactly what Ancona did, because it's really okay. He used Laplacian, and he had a way using what he knew on eigenvalues of the Laplacian in hyperbolic surfaces. He had a way in a really specific example with really specific constraints, which are really specific to Laplacian, to build an example of a surface with infinite genus, so geometrically infinite, with a finite point Margolis measure. And in fact, we were inspired by this example, but we realized that our work on gamma k and so on allowed us to build plenty of examples of surfaces with finite point Margolis Sullivan measure, which included Ancona example, but which were much more easier to build. I mean, and so what we call Ancona-like surface is maybe start from it's a family of construction more than a definition of a surface. And I would say start from a surface. So geometrically infinite surface, let's say S0 hat, with the critical exponent of the gamma 0 hat strictly less than 1. Okay, and the point is that it is possible for different reasons. It exists, and start from any example you want. Okay, you know that there are some. Choose one, and choose finitely many. I chose on my picture there is only one, but choose finitely many pair of pants. Pop for pair of pants on this surface, and then you pinch them, their boundary. Okay. And if you do that, you don't change the critical exponent of the new surface at infinity, or the gamma k hat will not move. My notation are bad, but this is a kind of critical exponent of a kind of fundamental group outside the compact set, if you can say that. It is a kind of heuristics. It's a fundamental group outside a compact set. it's not completely true, but it's the good heuristics. This, when you pinch a pair of points, this does not change. So it's certainly the same as the critical exponent outside the compact set for the group gamma 0 hat, which is less than the total growth of the group gamma 0 hat, which is strictly less than 1. But when you pinch, you get a surface whose entropy gets closer and closer to 1. So, and so it's really, okay, I'm not sure you are able to understand some, it's not so efficient as a blackboard, but it's really not a definition, a precise definition, but a kind of construction. You start
Okay,
from.
Thank you. Yeah.
I'm not sure. Is it clear?
Yeah, it's yeah, some idea.
Okay. So that's what we call Ancona-like surfaces, because Ancona's example inspired us to get this construction.
Any other questions? If not, let's thank Barbara once again for the lovely lecture.
Thank you.